In Chapter 3, we're going to start our unit on probability. And the first two chapters, I think, are really intro material, getting you familiar with some terminology, introducing the basics of sampling and types of samples and that kind of stuff. Chapter 3, I think, is the first chapter where we really start having to do some calculation, have to do some work to really understand the inner workings of what's going on. So a little bit of terminology at the beginning here. We have experiment. I think you have probably a general idea of what experiment is, but in statistics, an experiment is just a controlled study where we're trying to collect data in a controlled manner where we're taking a specific group of people or animals or groups of plants, or who knows what it could be, but we are controlling the variables such that we can hopefully try to make a connection between our independent variable, the thing we're changing, and the output. Okay, so experiments are done in controlled situations. I don't have it on this slide here, but the alternative to an experiment would be an observational study. Okay, in this, we're not trying to control conditions, we're just maybe asking survey questions. Okay, that's just an observational study. So this word outcome has a specific connotation when we talk about probability, and that is that the outcome is the overall result of an experiment. Okay, we're going to see in a minute we have events and we have outcomes. Okay, outcomes are typically more complex. It's talking about the full end result. So, for example, an event might be drawing a single card out of a normal 52 card deck, but the outcome might be the full 5 card hand that you have when you're playing a game. Okay, so one card, what you get on one card might be an event, what you get in the full hand would be an outcome. Okay, so there's just to kind of hopefully help you understand that difference. And then the sample space is all of the possible outcomes for an experiment. So when it comes to sample spaces, there's a couple ways that we might want to represent them. Okay, one way would just be to list all of the possible outcomes. And sometimes this is accessible, like if we're flipping a coin twice and we're recording all the different possible ways that could happen. Okay, there's only 4 outcomes there, so that's not too bad. But if, on the other hand, we're talking about maybe lottery tickets, right, and all the different possible combinations of numbers on lottery tickets, that would be, in the billions, and certainly not possible to list it. Again, a tree diagram is a way that we can list possible outcomes if, again, the number of outcomes isn't too high. And then the third way would be to create a Venn diagram. And the Venn diagrams are kind of nice because you can group a lot of stuff inside of a circle, and giving it a name. You don't have to necessarily list out every single item when you do a Venn diagram. So sometimes they're kind of handy. So let's look closer at that flipping a coin twice example. We want to know, what are the possible outcomes here? Well, the possibilities for the first flip would be heads and tails, and the possibility for the second flip would be heads and tails. So if you put all of those together, we could have heads, heads, which we would probably denote with like an HH. We could have heads, tails. We could have tails, heads, and we could have tails, tails. So 4 different possible outcomes, right? Each of those, like heads, heads, would be an outcome. A single head, heads, would be an event, right? So flipping it once, you get a head, that's an event. Flipping it twice, recording heads, heads, or heads, tails, or tails, heads, that would be an outcome. Okay, so the sample space is all the possible outcomes, so it would be those 4 things: heads, 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 tails, tails, heads, and tails, tails. All right, so here I am getting finally to the event thing. It maybe should have come a little earlier. This is actually probably not phrased correctly. I think what it should say is any combination of events, right, creates an outcome of an experiment. Typically, We use capital letters to denote events. Like typically we'll start with A and B, and if we need more letters, we'll go to more letters. If we want to talk about the probability of an event occurring, that would be P of A, P parentheses A. Now I think it bears defining what probability is. I think we've talked about probability briefly in chapter 1. Basically just said it's how likely something is to happen. And another way of thinking of probability is as the long-term relative frequency of a particular event. So, for example, continuing with the coin flipping idea, if you flip a coin 10 times, okay, you might get 3 heads and 7 tails, okay? Now we know, or I think intuitively most of the time we know that we should get about half of each, right? It's a 50-50 chance, we would call it. Well, when we say the long-term relative frequency of a particular event, we mean if we do it a whole bunch of times, then we should see it approach a particular value. Okay, so if you only flip a coin 10 times, you might get some kind of unusual results maybe, but if you flip that same coin 10,000 times, that would probably zero in on being a lot closer to 5,000 out of the 10,000, right? Now it's probably not going to be exactly 5,000, but it's going to be pretty close to 5,000, close enough that it's going to look like half, okay, or roughly half. So the long-term relative frequency, meaning if you do something a lot of times, that's going to be indicative of the probability. Really important thing to note here, probabilities are always between 0 and 1. You can never have a probability that's a negative value, and you can never have a probability that's bigger than 1. Okay, the reason for this is because if we say that the probability of something is 0, that means it never happens. Excuse me, that means it never happens. It's not quite accurate to say that it's impossible, but I wouldn't chastise you for saying that. You know, like from a mathematical perspective, probability of 0 doesn't mean something's impossible. It just means it never happens, which might sound like the same thing, but it's not quite the same thing. If the probability is 1, okay, that means that it always happens. Okay, you can think of that as it's basically guaranteed to happen. All right, law of large numbers basically says that if you do an experiment enough times, the relative frequency approaches the theoretical probability. Okay, by theoretical probability, think back to the coin flipping thing again. We know that about half of the time that we flip a coin, we should get heads, because the theoretical probability of flipping a coin and getting heads is 0.5 or 1/2. Okay, but like we just talked about, if we flip that coin 1,000 times, it may not be exactly 500. It might be 505 or something, right? But it's going to be pretty close to the theoretical probability, and the more times we do that procedure, the closer it's going to get, typically. All right, so there are times in probability when we use the word or. And or is a little bit of a tricky word because in math, or always means one thing. But in everyday life, or has 2 different possible connotations or denotations. We have the inclusive or and the exclusive or. And so I think we need to probably parse these out and make sure that we understand which of the 2 we're talking about. Okay, so think about these 2 statements. First one is, in order to get a degree from KSU, you need to pass a course in college algebra or calculus. Second statement, you can have soup or salad with your entree. In the first statement, do you think KSU would prevent you from getting a degree if you took both college algebra and calculus? Likely not. That would be weird, right? Why would they penalize you for taking extra courses? Okay, that's the inclusive or, meaning you have to take a course either in college algebra or calculus or both, right? You can take both and be okay. But in the second statement, that's the exclusive or, right? When you order at a restaurant, they ask you if you want a soup or a salad, and you could say both, but you're going to have to pay for it, right? But in terms of what comes with your entree, it's either a soup or a salad, but not both. Okay, so that's the exclusive or. Well, in math, we always use the inclusive. Okay, so the both would count. If we said, what's the probability of event A or event B, implied in that is or both. Okay, what's the probability of A or B or both? So always just keep in mind that when it comes to math, not just probability here, but also, you know, if you ever take a class in topology or set theory or number theory, or is always going to be the inclusive or. When it comes to and events, and means what it always means. Okay, there's no ambiguity there. It's and in daily life is exactly the same as and in math, so don't worry about it. Complement. This is probably a new term for you. You've heard of the word complement with an I, but a complement with an E is basically the opposite of a particular outcome. So the complement of A is A not happening. So we, as a notation for that, we use the little apostrophe, which we read it as a prime, so that would be A prime. Conditional probability is where we have two events, and we want to know what's the probability that event, for example, event A happens, given that event B has already happened. Okay, so if event A is for some reason affected by the outcome of event B, then we need to know that. So that's where this conditional probability comes in. Typically, this note here about conditional reduces the sample space. What this means is usually not all possible outcomes are available anymore because event B has occurred. Okay, so when we say reduces the sample space, that means there's not as many possible outcomes anymore. Quick example of that. Again with the coin flipping. If I want to know what's the probability of flipping heads and then heads. Okay, so what's the probability of the heads case? Then ordinarily that would be 1 out of 4, right? Because heads was one choice out of 4 possible outcomes. But if I rephrase, I said, what's the probability of getting heads given that the first coin flip is heads? Okay, well, there are only 2 possibilities that start out with heads, right? There's heads and heads tails. So now the probability of getting heads is only 1/2, not 1/4, because there's only 2 choices now. We know that we flipped a head on the first flip, so that means the only 2 possible outcomes are heads and heads tails. So now we'd say that the probability of heads is 1/2. Okay, so we do have a formula for this. Typically what we would do is find the probability of A and B and divide that by the probability of B. Alright, so we're going to switch over to my document camera, and we're going to work on example 3.1. It's pretty much straight from the textbook. I didn't change this one much, but if you would like, print it out. It's in Google Classroom in the same place where you could find the slides. You don't have to print it out. Maybe you make a copy of it in Google Docs and fill it out that way. But one way or another, be great if you had that worksheet available to kind of follow along with me. All right, so example 3.1 here on our worksheet is basically asking us some questions about basic probability. So to begin with, we're told that the sample space is the whole numbers starting at 1 and less than 20. So that would be numbers from 1 to 19. So when we list out S, it may seem a little tedious, but it's all of the numbers. Should have made my line longer. Between 1 and 19. Okay. Event A is the even numbers, and event B is numbers greater than 13. So to figure out A, we just need the even numbers between 1 and 19. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. Event B, numbers greater than 13. So 14, 15, 16, 17, 18, 19. And now we can look at some probability. So first of all, the size of our sample space is important when we're calculating probability. So we can pretty clearly tell there are 19 items in our sample space. And so the probability of A will be the number of things in A divided by the number of things in S. So 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers in A out of 19. So 9/19 is the probability of A. And we do the same thing for B. 1, 2, 3, 4, 5, 6 elements in B means we have a probability of 6/19. All right, A and B. Now I know that I don't have enough room in this line. I should have made it longer. But A, actually no, this one's okay. It's the next one that I need longer. So that's good, I can run out. A and B would be things that are in both. So the only elements that are in both would be 14 and 18. Nope, 14, 16, and 18. Right? 14, 16, and 18 show up in both. Okay, A or B is all the things that show up in A or B or in both. So 2, 4, 6, 8, 10, 12, and then 14, 15, 16, 17, 18, 19. Right? Each of these numbers is either in A or B or both. Like for example, 16 is in both. Right? All the rest, or not all the rest, but most of the rest are just in one or the other. All right, so now the probability of A and B is now 3 items over our original 19. And the probability of A or B is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 items out of 19, 12/19. All right, A prime. A prime is the complement of A, so it's everything that is not event A. Well, event A was the even numbers, so A prime would be the odd numbers. 9, 11, 13, 15, 17, 19. All right, probability of A prime is 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 of these out of 19. Probability of A plus the probability of A prime. So we're just going to add these two answers that we got. So the probability of A was 9/19 plus 10/19 for A prime, which is 19/19 or 1. It's an important little notion that we're illustrating there with that example. The probability of an event and its complement is always going to be 1 because something's going to happen, and it's either A or it's not A. Probability of A given B. So probably the best way to do this is to do, remember we have a little formula here, probability of A and B divided by the probability of B. So since we know all of those things, probability of A and B is 3/19 divided by the probability of B, which is 6/19. And when you flip and multiply, right, the 19s cancel out, you end up with 3/6 or 1/2. And then doing it the other way around, probability of B given A, we'll do the 3/19 again. That's the probability of A and B. But this time we'll divide it by the probability of A, which was 9/19. So again, we flip this one and multiply. The 19s cancel out. We get 3/9 or 1/3. So are these two equal? Is the probability of A given B equal to the probability of B given A? No, it's not. Okay, one of them is 1/2, the other is 1/3. All right, so several kind of important ideas illustrated there. Two of the highlights would be probability of A and A prime is 1, and that the probability of A given B is not always equal to the probability of B given A. Can be, but it's not in any way required to be. All right, thank you very much, and we'll go back to our slides. Okay, suggested homework for 3.1 all comes out of the practice section. This is obviously a little bit bigger set of homework problems than what I've been giving you so far. But there's more types of questions to ask, and so I think this will help you be prepared for the quiz that's coming up.